Hi everyone, welcome back to my channel Simony. It's me Vaishak. Today we are going to discuss about two-dimensional motion in which we'll be exploring projectile motion in very detail. Okay, good. Now what is a projectile motion? You can see it everywhere actually, right? When you kick a football, it's a projectile motion basically, right? And let's say a sniper is shooting a bullet, that's also a projectile. There are different kind of projectile motion. We are going to explain that also. And in general, a projectile motion is a motion in which a body experiences only gravitational force. For physical analysis, we are neglecting the air resistance. That means acceleration is constant and it is given by 9.8 meter per second square downward direction. You may think how the sniper bullet follow a projectile. It experience actually, even though the speed is very high, it experience the acceleration downward, and there is a slight downward motion at the end actually. So the shooter has to adjust that extra vertical motion downward, even though it is small, because that small variation can miss the target. Correct. We are going to discuss that one. Okay. Right. Now let's discuss types of projectile motion. Here we are going to discuss about two types of projectile motion. One is oblique projectile motion and the other one is horizontal projectile motion. What is this oblique projectile motion? The body must have initial velocity with angle greater than 0. Good. For example, a football kick. Now, in the case of horizontal projectile motion, the angle of lunging is 0, and that lunging happens at a height actually. For example, a diver running forward and jumping off a cliff to the river or pond. Okay. Good. So first, let us discuss about oblique projectile motion. Here, we can see that the initial angle of launch is theta degree and initial speed is v0. Remember, uh, initial velocity is v0 vector. This v0 vector has two components, v0x and v0y. Good. Now, as the projectile is moving, the velocity will vary, of course, because of the acceleration. And remember, at any moment, acceleration will be always constant and it is acting downward. So we can write a equal to negative g j cap, where j cap is the unit vector in the positive y direction, and that we have discussed long before, right? Good. Now, in this case, for this projectile, we have certain objectives. First, we are going to find a relationship between x coordinate and y coordinate. That means after a certain time, what will be the x position and what will be the y position. This is very important. For example, in the case of missile launch, then the computer has to know where the missile is, right? So one way to know is the horizontal distance and the vertical distance. Now, of course, for an artillery or football case, let's say, we have to know the range, correct? How far it will go. And also we have to know maximum height. This is very important for artillery because, if you want to fire an artillery from the mountain side, you have to know how much high it can go, or else it may hit the mountain top or even before the mountain top, right? Good. Now we have to know what is the time of flight also, how much time it will take to hit the target. That's very important, correct? Good. So we'll be tackling these things one by one. Good. So better we split this problem into two problems. Basically, we'll be looking x component independently and y components independently. And remember, the acceleration is only in the vertical direction, that means in the y direction. So x direction doesn't have any acceleration, so that direction physics is going to be very simple, but vertical physics is going to be little bit complex. Not that much complex, little bit complex. Okay, good. In the x direction, we can use the equation of motion 1 that we have derived in the motion in one dimension video, right? And Remember, in the x direction, we can transform that equation into Vx is equals to V0x plus Ax t, where change in time we can call it as time itself, because anyway initial time is 0, and V0x is the initial x component. We have denoted that here, correct, with the red marking. And remember, as the acceleration along the horizontal direction is 0, that term will be cancelled out. So Vx is equals to V0 cos theta. Good. Now we can apply the equation of motion to x of is equals to xi plus vi delta t plus half into a delta t square. And here xf is x coordinate. Initial position is of course 0 because we are launching from the origin. Good. Right. And initial speed is v0 cos theta in the x direction, and the acceleration term will cancel out because acceleration is 0. Therefore, x is equals to v0 cos theta t. And this will be useful to find the relation between x and y. Okay, right. Let's mark that equation as equation number 2 and this equation as equation number 1. Great. Now in the y direction, we can do the same thing. We will apply the equation of motion 1. Vf is equals to Vi plus A delta t. So we can transform into component format. So Vy equal to V0y plus Ayt. By the knowledge of vector components, we can write V0y as V0 sine theta, correct? And Ay is negative g, so Vy is ultimately V0 sine theta minus gt. Good. Now we can apply the equation of motion to y equal to y0 plus v0y delta t plus half into ay delta t square. Now remember, we just replace the x variable to y variable. That's it, no other change. Okay, so y0 is 0 because anyway we are starting from the origin. The origin is 0 comma 0, right? X is 0 and y is 0 at origin, correct? So y equal to y0 plus v0 sine theta t minus half gt square. Therefore, y equal to v0 sine theta t minus half gt square. We can call it as equation number 4. And we can combine this equation number 1 and 4 to get a relationship between the y coordinate and x coordinate. So from the equation number 1, we can write t equal to x divided by v0 cos theta. Okay, so we can substitute that t into equation number 4. This t is unknown, we don't know the time, right? So t is related to the x position as t equal to x divided by v0 cos theta. So substitute that in y equal to v0 sin theta x divided by v0 cos theta minus half into g into x square divided by v0 square cos square theta. Right. Now sin theta divided by cos theta is anyway tan theta, and this v0 cancel out, and on the second term we can take the constant outside and write g divided by 2v0 square cos square theta into x square. Now remember, this equation in the format y equal to ax minus bx square, which is definitely is a parabola, right? So hence we prove that it's a parabola. Okay, of course the shape is like this, so it's a parabola, right? Good. Now let's find out maximum height. At maximum height vy equal to 0. Why is that? Because it is a turning point. If you only look at the y motion, the y is reducing and finally becoming 0, and it is increasing in the negative direction basically, right? That means the velocity is initially positive and reducing the value and becoming 0. Then after that, the velocity in the y direction is increasing but in the negative direction. Okay, good. And therefore, using equation number 3, we can find the time at which the projectile reached the height. So just we will substitute Vy equal to 0. So 0 equal to V0 sin theta minus gt. So by rearranging, we can write t equal to V0 sin theta divided by g. Good. Remember, this time is the time at which the projectile reached the maximum height. So we can substitute that in the y equation to get the height. At that time, y will be equal to h. Therefore, we can write h is equals to v0 sin theta into v0 sin theta divided by g minus half into g into v0 sin theta divided by g whole square. Good. Right. Now on rearranging, we can write in similar format: h is equals to v0 sine square theta divided by g minus v0 sine square theta divided by 2g. So we can take the v0 square sine square theta by g as common, so it will become v0 square sine square theta divided by g into 1 minus 1 by 2, and ultimately the height is v0 square sine square theta divided by 2g. Good, right. Now what is this time of flight? A projectile is launched at the origin, right, and it travels to a target on the x-axis, which is at a distance range, correct? So when the projectile hit the target on x-axis, y equal to 0, because vertical distance finally is 0, right? Thus equation number 4 gives 0 equal to v0 sine theta t minus half gt square. That means on rearranging, v0 sine theta t equal to half gt square. So v0 sine theta equal to half gt, because 1 t cancels. Okay, that time corresponds to time of flight. So t equal to 2v0 sine theta divided by g. Good. And remember, we have found a similar equation before. If you look at here, this is a time corresponds to maximum height. That means the time required to reach the maximum height is half of the time of flight, and that makes sense, correct? Good. Now let's find the range. Range means the horizontal distance towards the target. So when t equal to t, that means when the time is time of flight, x coordinate must be r, that is the range. Therefore, equation 1 gives r is equals to v0 cos theta into t, capital T. We are replacing the small t with the capital T. So that capital T we already found, so we can substitute v0 cos theta into 2v0 sine theta divided by g. So using mathematical identity 2 sine theta cos theta equal to sine 2 theta, we can convert this equation as r is equals to v0 square sine 2 theta divided by g, correct? So that's it. So our objectives are fulfilled. We found the relation between x and y, we found the maximum height, we found the time of flight, and also we found the range. These are essential for a projectile motion. Now let's focus on horizontal projectile motion. Horizontal projectile motion is very much related to oblique projectile motion, and the only difference is the angle is 0 and it is launched at a specific height from the origin. That's what written here. Projectile is launched in horizontal or x direction from a height h, and you can look at this diagram. The projectile is launched from a height h, and you can see it is following a parabolic path, and we are going to again prove that indeed horizontal projectile motion is parabolic. Okay, right. So it's launched with the initial speed v0, and finally it will reach a range r. So remember, initially the position of the projectile is 0 comma h, x is 0 and y is h. Okay, good. Acceleration is always downward. Good, right? That's what mentioned here. At any moment the acceleration will be downward with equal magnitude g, right? Good. Now similar to the oblique motion, we can split the problem into two problems, basically x problem and y problem. So in the x direction, acceleration is 0, x is equal to 0, and initial speed in the x direction is v0. Good. And remember, initially it doesn't have any y component, it has only x component, but as it travels, because of the downward acceleration, it will get negative velocity component. Okay, good. So we are going to discuss in the y problem. So right now let's apply equation of motion to get the position at any time. So x is equal to 0 plus v0 t plus half x t square, and initial position is 0. So you can write x is equals to v0 t, because x is 0, so this term will become 0. Good. Very simple. That means x varies linearly with respect to time. Now, equation of motion 1 will give you Vx is equal to V0 plus Ax into t, and of course the second term will cancel out and will give you V0. That means at any moment the horizontal component of velocity is, see, in the y direction the acceleration is negative g, and initial velocity component in the y direction is 0, and initial y position is h, right? We are launching from a height h. So equation of motion 2 will give you y equal to h plus 0 t minus half gt square. So y is equals to h minus half into gt square. Let's put that equation number, let's consider that as equation number 2. Good. Now, equation of motion 1 in the y direction, if you apply, you will get Vy equal to 0 minus Gd, or Vy is equals to negative Gt. That means velocity in the y direction is linearly varying with respect to time. Okay, right. Now, as in the case of oblique projectile motion, for horizontal motion also we can find the relationship between x and y. For that, we can combine the equation number 1 and 2, and it will give you y equal to h minus half into g into x minus v0 square. Remember, we are just replacing t with the x divided by v0. Okay, right. So that means y is equals to a minus b, y equal to a minus b x square format we are getting, correct? So that format is nothing but a parabolic equation. I am telling in different ways, so let me clarify. So the most general expression for parabola is y equal to a plus bx plus cx square, and here remember bx term is absent. Okay, that bx term was there in the oblique case, but here the bx term was not there, and a term is here h, but in the oblique case there was no a term. Okay, right. Now let's focus on time of flight. At the moment when t equal to time of flight, equation 1 will become 0 equal to h minus half into gt square. Why is that? Of course, when it reaches the x-axis, the y will become 0, correct? Good. So we can rearrange half gt square equal to h. So t square is equal to 2h divided by g. Therefore, t equal to square root of 2h divided by g. Now, finally, let's focus on range. So when the projectile lands on the x-axis, the equation number 3 becomes 0 equal to h minus g divided by 2v0 square into r square. Okay, remember equation number 3 is this one, this parabolic equation. Okay, good. So therefore we can write r square is equal to 2h v0 square divided by g. So taking the square root on both sides, you will get range is equals to v0 into square root of 2h divided by g. What is the meaning of it? You can increase the range by increasing the speed of launch, or you can increase the height so that you will profit time, so thereby the effect will be increasing range. Okay, that's it, folks. We have discussed about projectile motion in detail. All the simulations I have attached below, please refer that. In the next video, I'll be doing a lot of problems in projectile motion. Have a great day. Take care. Bye bye.